instructing a computer in a language that with a little translation it can comprehend. Similar to how you could have a recipe on how to cook something, you offer computers instructions in what is referred to as code. You tell the computer about elements it needs to work with, like the ingredients, you give it instructions, and there might be some conditions it needs to choose between, like choosing whether an oven is electric or gas, and then following the corresponding temperature. So in this video, you will learn about coding schemes, binary code, integers in computer, and operation on binary numbers.
ASCII uses 7 bits. In other words, the binary number representing these letters have 7 bits to them. So we can use 7 columns to create a possible 127 different number of each, which has a number or letter symbol associated with it. So if we take a 7 bits like this, we can create a binary number using 64 and 1 to create the number 65, which represent A. So this is the binary representation of the letter A or your keyboard. With 127 different possible number, we can represent all of the uppercase letter, all of the lowercase letter, all of the digits 0 to 9, as well as a wide range of a symbol. Additionally, there are also represented battery number, so the backspace button, escape tab, the enter key, and also the delete button, which actually is the number 127, the maximum that the ASCII can represent. However, there is a problem because whilst this 127 different symbol and characters seems fine, they fall for short of all of the number of the character that we need to represent. This language, for example, are not represented is a standard ASCII. So how we can represent all these different character and symbols, as well as the wide range of emojis or whatever you can call them. Standard binary coded decimal interchange code, or what we call ABCDEC. It is a binary code for alphabetic numeric character that IBM developed for its largest system. Internet Business Machine, or what we called IBM, started in 1911 as a producer of punch card tabulating machine. IBM came to dominate the new field of mainframe and main computer. It has 8 code, 4 bits for zone, 4 bits for digit, and also 28 is equals 256 combination and represent 256 unique symbols. It is used mainly in mainframe computers.
The answer is that we use Unicode. Now, Unicode is exactly the same thing as ASCII for all of the characters 0 to 127, but Unicode can use more bits than ASCII, and so it can represent a wider range of different symbols, so it can include all of the alphabets, a much wider range of symbols, as well as a wide and growing range of emojis. So just to recap then, ASCII is an encoding system for letters on your keyboard that uses 7 bits. We can use the 8, but occasionally which we call extended ASCII, which doubles the number of possible characters, although that's still far short of what we need for the full set of languages and symbols that we used. Unicode is the same thing as ASCII for the first 127 symbols or characters, and Unicode can support far more characters by using 8, 16, or even 32 bits, which would allow the support for 2,147,483,637 different possible characters. That's a lot of emojis.
Imagine trying to use words to describe every scene in a film, every note in your favorite song, or every street in your town. Now, imagine trying to do it using the only numbers 1 and 0. Every time you use the internet to watch a movie, listen to music, or check directions, that's exactly what your device is doing using the language of binary code. Computers use binary because it's a reliable way of storing data. For example, a computer's main memory is made of transistors that switch between either high or low voltage levels, such as 5 volts and 0 volts. Voltages sometimes oscillate But since there are only two options, a value of 1 volt would still be read as though that reading is done by the computer's processor, which uses the transistor states to control other computer's devices according to software instructions. The genius of this system is that a given binary sequence doesn't have a predetermined meaning on its own. Instead, each type of data is encoded in binary according to a separate set of rules.
Let's take numbers. In normal decimal notation, each digit is multiplied by 10, raised to the value of its position, starting from 0 on the right. So 84 in decimal form is 4 times 10 to the 0 plus 8 times 10 to the first binary numbered notation works. Similarly, but with each position, based on 2 raised to the sum power of 84 would be written as follows. Meanwhile, letters are interpreted based on standard rules like UTF-8, which assign each character to a specific group of 8-digit binary string. In the case of 01010100 correspondence to the letter T. So how can you know whether it's a given instance of this sequence is supposed to mean T or 84? Well, you can seeing the string alone, just you can tell what the sound da means from hearing it is isolation. You need context to tell whether you are hearing Russian, Spanish, or English, and you need similar context to tell whether you're looking at binary numbers or binary text. Binary code is also used for far more complex type of data. Each frame of this video, for instance, is made of hundreds of thousands of pixels in color image. Every pixel is represented by 3 binary sequences that corresponds to the primary colors. Each sequence encodes a number that determines the intensity of that particular color. Then a video driver program transmit this information to the millions of liquid crystals in your screen to make all the different hosts of you now sounds in this video is also stored in a binary with the help of technique called plus code modulation. Continuous sound waves are digitized by taking snapshots of their amplitudes. Every few milliseconds, they are recorded as number in the form of binary string with as many 44,000 for every second of sounds. With they read by your computer audio software, the numbers of determine how quickly the coils in your speaker should vibrate to create sounds of different frequencies. All of this requires billions and billions of bits, but that amount can be reduced through clever compressions format. For example, if a picture has 30 adjacent pixels of green space can be recorded as 30 green instead of coding each pixel separately, a process known as run length encoding.
An integer is just a whole number like 1, 3, or 6. If the number has any fractions or decimals, then it's not an integer. Integers are whole. Let's look at another example. Mo has 1 treat. 1 is an integer and we can store it on a variable. But when she's a good girl, she might get 2 or 7. The variable treat stays the same, but the integer value it stores can change. This will also change the outcome. A computer program for a game stores a lot of information as integers, so number value can change or update while you play. Look, you have an integer rank and coin count right here in the codable. This is an example of a game program storing an integer value that represents something like your score.
In mathematics, a binary operation or dyadic operation is a rule for combining two elements, called operands, to produce another element. More formally, a binary operation is an operation of arithmetic 2. You can add, subtract, multiply, and divide binary numbers using various methods. These operations are much easier than decimal number arithmetic operations because the binary system has only 2 digits, 0 and 1. Binary additions and subtractions are performed as same in decimal additions and subtractions. To add binary numbers, let us remember the following magic table. To subtract binary numbers, then, let us use the following magic table. To multiply binary numbers, we will do the same process as decimals. Lastly, in dividing binary numbers, we will use the same process as in decimals.